Hi. In this short presentation, I'm going to focus on propulsion part of hypersonic flight. My name is Narari K. Hunsur. This video is available in the following areas: GitHub and Blogspot. You can also contact me at this Gmail, narahari.rues@gmail.com. So, a brief recap propulsion system. Subsonic transport aircraft like the large Airbus and Boeings you see, they all use very high bypass turbofans because these have very high fuel efficiency. Low supersonic on a flight like Mach less than 2, typically combat aircraft like Mirage 2000, Rafale, or Tejas. They use a low bypass turbofans or turbojets themselves. High supersonic, somewhere between Mach 2 to Mach 4, cruise missile, for example, ramjet is the preferred mode of propulsion. For hypersonic flight, what we need to do is scramjet. In hypersonic propulsion, key challenges are supersonic combustion, basically flame stabilization, and high thermal load. Turbojets and turbofans, typically used in airlines and fighter aircraft, use rotating compressors to pressurize and slow down the air to subsonic velocities to enable combustion and produce thrust. Combustion in these systems relies on a low speed flame propagation. So, even at moderate supersonic speeds, the compression is achieved by augmenting turbojets with variable geometry intakes and air bleeding systems and such. However, as the Mach number increases, these become inefficient. For supersonic flight, traditional jet engines cannot be used directly for propulsion because shock waves generated when they impact on the compressor blades they can damage. So these are then paired with intakes which have ramps like the one you see on the right, which is an intake which was used in Concorde aircraft, which was flying sometime around 1976. It's a Mach 2.2 transport aircraft. So these create oblique shock waves which slows down the flow, oblique shock waves followed by normal shocks to flow to subsonic speeds for efficient operation of jet engine. This is, however, effective only till around Mach 2, after which the efficiency drops because of losses due to shocks. So, if you look at the overall propulsion efficiency in terms of specific impulse, you can see that at low Mach number, up to around 2 or 3, turbojets and turbofans are there. After that, ramjets become more efficient, and then followed by scramjets, and in future, possible new types of propulsion systems. Rockets, as you see the red line here, they operate right from static condition up to Mach 20 with the same kind of specific impulse, but their efficiency is very low. Of course, if you are at very high Mach number, you don't have a choice. You have to use rockets. So if you look at the fundamental equation of thrust, which is applicable to all types of propulsion systems, ramjets, turbojets, propeller-driven, chemical, electric, what you see here is fluid enters the system at a velocity v naught with a mass flow rate dm by dt, exits at a velocity ve, and mass is added to the outflow at a rate dmf, mf meaning fuel mass rate, flow rate. Thrust is simply the change of momentum and a pressure term. So as I said earlier, this holds for all propulsion systems. So in an air breathing propulsion system, net thrust is what we are interested in. Net thrust is defined as nozzle thrust, that is thrust produced by nozzle, minus the drag due to flow inside the engine. Net thrust is what accelerates the vehicle. So drag due to flow through the engine is very sensitive to flight Mach number. As flight Mach number increases, net thrust sensitivity also increases faster. Typically, for example, at Mach 8, a small error of 5% in the nozzle performance leads to a reduction of 35% in the net thrust. So nozzle design becomes an extremely critical part as Mach number increases. So let's have a quick recap of ramjets, which are operating right up to Mach 4. In a ramjet engine, initial compression is directly operated inside the air inlet, which by slowing the flow raises the pressure without any compressor, which means you avoid all moving turbomachinery components. Efficient only when the natural compression provided by inlet is high enough, typically Mach number 1.52 and above. So ramjet systems are not self-starting, so need an additional propulsion for acceleration. So rocket propulsion is usually used to accelerate them up to about 1.5, then the ramjet can take over. So this is the kind of propulsion system used in BrahMos missile. So if you look at the schematic, what you see here is the intake ramp. So you have a oblique shock, multiple oblique shocks, slow it down, and finally terminated by a normal shock to bring the flow inside the combustor to subsonic conditions. So basically here, the primary and secondary fuel injectors are there. Flame stabilizers in combustors. Combustion Mach number, as I said, is subsonic, around zero point 0.4. Typically, the residence time is about 4 to 5 milliseconds. So in 4 to 5 milliseconds in combustor, the combustion has to be completed, gas is generated, and then efficiency follows from that. Followed by a conversion diversion nozzle. As I said, this is a subsonic here, so you need to have a conversion diversion nozzle to accelerate it further. Air cooled or ablative line combustor nozzles are a must because the temperatures are very high. So soon as the starting point is reached, the ramjet engine is efficient up to about 3.5 to 4, and due to the high temperature and pressure, combustion chamber, good combustion conditions are seen. In a conventional ramjet, airflow is slowed down from supersonic speed down to about Mach 3.4 or 3 at zero point 0.4. So shocks created by the forebody and the compression ramps of the air inlet raise the temperature and pressure as mentioned in the previous slide. Low speed and high temperature provide a very good favorable condition for injecting, mixing, and burning of fuel. However, the shock system is also a source of entropy losses, which implies that the pressure losses are there with increased temperature. And these temperatures become very high at the entrance of the combustion chamber, which implies internal structures are exposed to high thermal loads. Heat addition to an already hot stream becomes less efficient. So this decrease in efficiency of ramjet performance starts at around Mach point 0.5, so that its operation is very limited above Mach 5. An alternative to circumvent this, an alternative to circumvent this is what is called a scramjet, um, which the in the flow in the combustion chamber is not slowed down to subsonic conditions, but it is right up to it's still supersonic, but a low supersonic. Key difference being the inflow to combustion is supersonic. Scramjet powered aircraft carry fuel on board and obtain the oxidizer by ingestion in the atmospheric conditions. As compared to rockets, which carry both fuel and an oxidizing agent, this requirement limits scramjets to suborbital atmospheric propulsion, where the oxygen content of the air is sufficient to maintain combustion. So similar to ramjet, forward velocity causes the air to compress within the inlet in a scramjet. Scramjet is composed of three basic components: a converging inlet, where incoming air is compressed; a combustor, where gaseous fuel is burned with atmospheric oxygen to produce heat and gases; and a diverging nozzle. Since the flow is already supersonic, you need only a diverging nozzle, where the heated air is accelerated to produce thrust. Similar to a ramjet, scramjet does not use compressor turbine combinations and also is not self-starting. Similar to a scramjet scheme, you can see here you have a series of oblique shocks, but they are not terminated by a normal shock, which means the flow in the combustor is still supersonic. And you have strut and wall injection, strut and wall resist flame stabilization, all that thing. So far for hypersonic flight, two broad systems have been employed: pure rocket propulsion, solid or liquid, what you can see in, for example, Agni and other kind of ballistic missiles, and of course, rocket plus scramjet. Rocket initially to accelerate it to that speed where the scramjet takes over. Rocket propelled craft, can operate independent of the atmosphere as they carry oxidizer on board, suitable for ballistic missiles and long-range ballistic missiles. However, their range and payload capacity is limited as the propellants form a large part of the takeoff mass. Scramjets utilize atmospheric oxygens, hence can carry a larger payload with a higher range capability, suitable for surface to surface cruise missiles. However, their applicability is limited to suborbital flight. There have been cases where a rocket and a ramjet or scramjet have been combined, as you can see here. There is a primary rocket which produces fuel rich gases, and the air which comes from the air is supersonic mixed, and then you have additional fuel injection and then exited from nozzle. And this, while in theory is a very useful and simple combination, but it has lots of technical and mechanical challenges. Of course, people have been doing a lot of research on this kind of thing. So now let's look at the fuels typically for ramjets and scramjets. Hydrocarbons like GP7 a type of kerosene, or characteristically they are very unstable. At some elevated temperatures, they decompose instead of combusting or burning. They decompose, resulting in coking, plugging of passages, and ultimate failure of engine systems. There is a class of endothermic fuels which absorb a lot of energy and heat and decompose without forming surface deposits. Endothermic decomposition can occur thermally due to exposure to high temperature, can be promoted with a catalyst. Some such examples are decalin, methyl cyclohexane. Another popular fuel used is hydrogen, both in gaseous and liquid form. Hydrogen, being an element, exhibits dissociation to monatomic only at very, very high temperatures, so which is suitable for this kind of propulsion. Liquid hydrogen is very effective for active cooling of vehicle structures, which is an important requirement for high speed flights. Hydrogen ignition and combustion is rapid enough that scramjet combustion is possible over a reasonable length. Ignition and combustion is possible at rates 10 to 30 times higher than flames using gaseous light hydrocarbons at typical temperatures. It is a preferred fuel for air breathing scramjets based on reactivity alone. So here are some references: Propulsion Systems for Hypersonic Flight by Francois Falempin from MBDA, Yvette Levias Hypersonic Air Breathing Propulsion, Hypersonic Air Breathing Propulsion, Heiser and Pratt, and a book written by my professor H.S. Mukunda, Understanding Aerospace Flight. Thank you, and thank you for listening to me.